Hi guys, welcome back to my channel. So today we'll start our topic on measurable functions and the Borel sigma algebra. So now before we do that, we need to ask ourselves that why are we delving into the Borel sigma field and what is it that the Borel sigma field offers over the measurable space big omega comma f, where f is the sigma algebra or the sigma field of big omega. So to answer that, let me give you an example. We learned that our set F, which is the sigma field on the set big omega, well, it has some sets. Let's say it has a set A, B, C, right? Now we want to impart some numeric value, some real value on this. It could be a probability, it could be a number ranging between 0 to 1000 or minus infinity to infinity. We want to impart a real value on this set. How do we do that? So our next goal is to develop the tools to measure the likelihood that the events collected into the sigma field in the previous videos occur. All right. While we will work directly with the measurable space, which is this big omega f, distinct advantages can be gained by transferring our investigations to the richly endowed real numbers. To be successful, such transfers, which honestly occur very frequently within mathematics, they occur in linear algebra, where you transfer linear mappings and linear transformations to a linear algebra field, right? We must preserve the structure under consideration. This means that both the source and the target spaces must be endowed with similar structures and mappings, which make the transfer must preserve the main ingredients of the structures. All right, so we want to transfer our sigma field and the set big omega to the real number space. All right, now we need to do this in a way that the structure of this is preserved. It does not break any of the rules of the sigma field that we described in the very first video, right? So how do we go about doing that? Let me show you. Okay, so the structure that we are considering here is the sigma field, all right? And the appropriate mappings are called measurable functions. Okay, measurable functions are the mappings that we'll use to move from our sigma field, which is this, to a sigma field that consists of real numbers. And we need to choose a sigma field on R, right? R is a set of all real numbers. The most natural subsets of R which can be measured are intervals on a real number line, right? If I have a real number line between, let's say, 0 and 1, then this set of values, let's say between 0.25 and 0.75, can be considered a subset of R. And the most natural subsets of R which can be measured are intervals, and at minimum, our sigma field must contain the intervals. On the other hand, the smaller the sigma field on R, the larger the collection of measurable functions. Okay? So I'm going to define the sigma field here and the mapping. So I would request you all to listen to this definition very carefully. I'm reading it from my notes, but you need to listen to the words one by one to actually understand how we are making that mapping from your sigma space using a measurable function. All right. So I'm going to define the Borel field. The Borel field on real numbers R, let's call that Borel field B of R, is a sigma field generated by the open intervals in R. All right. Subsets of R which belong to B of R, subsets of R which belong to B of R are called the Borel sets. Borel sets. Okay, so let's go through this once again. The Borel field on R, P of R, is a sigma field generated by the open intervals in R. Subsets of R which belong to B of R are called Borel sets. Okay, so now let's say instead of this omega, I have the real number line between 0 and 1. And I have open sets over here. Let's say I have one set 0.25 to 0.75, and then I have another set over here from 0.1 to 0.6. If I want to form a sigma field on this, that sigma field will be called B of R. Okay. If I want to form a sigma field on this using real numbers, now you need to understand that the set here aren't discrete values. Unlike what we learned over here, it's not a comma b comma c, it's a real number which has a range of values in the open set. And applying the same rules of the sigma algebra that we learned in the very first video, we form the Borel field B of R. All right. Now subsets of R, like let's say 0.1 to 0.6, 0.25 to 0.75, and the other subsets which belong to B of R are called Borel sets. So like these sets that you have here, right, these events that we call them, these events are called Borel sets, okay, in the Borel sigma field. That's something we need to keep in mind. Okay, so guys, I'm actually going to describe the measurable functions, all right. Now that we know what Borel sets are, I'm going to define what a measurable function is. So let me take a point omega, all right. Omega is just another point that belongs to the set big omega, okay. Or this, let's call it W to keep it consistent. Let's call it W. And this W is just another point in our big omega, okay. So now I'm going to propose something. I'm going to write a proposition here. Proposition. And let me just write down here. Let X. Okay, so let me explain this proposition here. Let X, where the function or the random variable X maps big omega to the real number line, denote a real valued function. Okay, this is a real valued function. We later see that this is a random variable, but for now, let it be called a real valued function, a function that maps big omega to the real number line. Okay, the collection of sets X inverse B, where B ranges over the Borel subsets of R, is a sigma field on big omega. We call the sigma field f of x and call it sigma field generated by X. All right. So I just want you guys to read this once again slowly and try to understand what this sentence is saying, all right? What this proposition is saying. And I'll explain it right now. So basically, when we started this video, I told you that we want to map all the sets in omega to a real number line or some sort of real numbers, right? Because then we can assign probabilities or some values to our events. That's exactly what we're trying to do now. We have a function X that maps the events in big omega. Big omega, again, as I've repeated over and over again, is a set of all the possible outcomes in our entire time frame of observation, all right? So X is a function that maps big omega to the real number line, okay? Let me call this real number line. And depending upon what point we pick, let's say if we pick x omega xw1, it falls over here. If we take x omega 2, maybe it falls over here, x omega 2, x omega 1, and where omega 1, omega 2 are some points in the set big omega. All right. So depending upon the values that we get on the real number line, they will be a Borel set, right? Because as we've learned that every set on the real number line can be a Borel set. So the Borel's so this set will map to the Borel sigma field, right? That's what we learned in the previous definition over here, that there's a Borel sigma field for every Borel set on the real number line, right? So for every point omega 1, omega 2 in big omega, the real function maps it on the real number line, x of omega 1 or x of omega 2, and this gives us our Borel sets. These Borel sets map to the Borel sigma field, all right, such that if I take x inverse of the Borel sigma field, I get a map back to my sigma field in discrete time. Okay, so what this is basically saying is that if I have a Borel set on the real number line and I map it to the Borel sigma field, if I take the inverse of that function, it should map back to some event in f of x. Okay, if I have some event a comma b comma c here, then every x of omega 1 or x of omega 2 that maps to the Borel sigma field, the inverse of it will map to the event in f of x, all right? And we call this the sigma field generated by x. So if I have some value for this Borel sigma field and it maps back to this event, to the set of events, I can assign it a value, right? If I have a simple measure on the real number line, let's call this a real number line between 0 and 1. Okay, and x of omega 1 maps to values between 0.1 and 0.3. X of omega 2 maps to values between 0.6 and 0.8. If x of omega 2 maps to b of r, which is the Borel sigma field, and I take the inverse of it, and that inverse gives me an event in f of x, let's call that event a comma b comma c, I can assign it a value where the value might be 0.8 minus 0.6. This, by the way, is called the length measure, and it can be used to assign a probability value, which is 0.2. So there's a 0.2 probability that I get this set back in the sigma field. Now this is just an example. I'm not saying that this is the probability. We'll come to this in the next chapter. What I'm trying to explain is I can map the real number line using this measure that we learned right now, right, to the event in our f of x, which is what we want to do. We want to map discrete to continuous, okay? Because then we can open our analysis to probabilities. And that's exactly what I'm trying to do. And I have to keep this consistent in a way that this B of R, which is the Borel sigma field, it also is consistent with the rules of the sigma field that we learned in the second video, right? You remember the rules of the sigma field, that sigma belongs to F and A complement belong to F, and the union of A n, where n equals 1 to n, they all belong to F, right? So this Borel sigma field has to be generated in a way that it's consistent with these rules of the sigma algebra or the sigma field. So so there is a proof for this. I mean, I can prove this if you want, that the Borel sigma field is consistent. So I'll tell you what, I'll prove the first one right now and the second one right now. The third one, I want you guys to try and prove it yourself, okay? Yeah, and if in case you don't get it, just leave a comment down in the comment section below, and I'll put a proof. I'll put it up in a separate video, all right? So first, I'm going to prove that this real number line is consistent with the fact that it is consistent with this, okay? So I'm mapping my entirety of big omega to R. Now I told you if I take a point x of omega 1 where omega 1 belongs to big omega, then x of omega 1 will give me a point. Let's call this real number line between 0 and 1. It'll give me a point between 0 and 1. Let's say it gives me some point over here, right? 0.4 and 0.6. So if I take the whole big omega, which is my entire set of observations, it maps to the entire real number line, right? Not just some set on the real number line, but the entire real number line. Correct? It can be 0 to 1, it can be 0 to infinity, anything, but it maps to the real number line. So if I take x inverse r, this will belong to f of x, right? Because the real number line, the entire real number line is also a Borel set. And this, since this belongs to f of x, our first criteria is satisfied. Okay, so we have proved that it's consistent, right? So because I'm running out of time right now, I've proved the first one. I'll also leave the second one for you guys to try and analyze yourself, the second and third one. And if you, in case you don't get it, just leave a comment in the comment section below and I'll put another video for this, all right? So I hope you all understood this, where if I map the entire omega, the set of all observations to the real number line, the real number line in itself is a Borel set. So if I take the inverse of it, it maps me back to my entire sigma field, f of x. The sigma field generated by the Borel sigma field, all right, f of x. And hence we've proved that, that this definition of ours, this Borel sigma field definition of ours, is consistent with the definition of the sigma field that we learned in the second video, all right. Okay, so now let's look at measurable functions with an example, all right? And the most simplest and the easiest to understand measurable function is an indicator function. So I'll explain what an indicator function is. An indicator function of a set A in big omega, IA, okay, this is called an indicator function, is defined as follows. If I have IA of omega, and if omega belongs to a set A in big omega, then I get the value 1. If the small omega does not belong to the set A, then the indicator function gives me a value 0. Now, the value of IA at omega indicates whether or not omega belongs to A, correct? So when we examine IA inverse of B, where B belongs to R, B is the Borel set over here, we are considering all points mapped into B, alright? And the only relevant information is whether or not 0 or 1 or both belong to B. For any B that is a subset of R, we have the following possibilities, right? So I don't know if you, so let me just explain this with another diagram. So I have some point omega, and this omega points somewhere in this set big omega. So when I take IA of omega, okay, this points to the Borel set in this on the real number line, all right, and all that we are concerned about is whether this points to 1 or 0, okay, because we are considering I of omega. This, okay, I of omega is our measurable function. So all that we are concerned about is whether it points to 0 or 1, okay, because wherever it points, if it points to 0, then 0 is what enters the Borel sigma field. If it points to 1, then 1 is what enters the Borel sigma, 1 is the part of the Borel sigma field. And if it points to both 0 and 1, then then omega is basically the entire set big omega. So that's what I've done here. If IA inverse of B is equal to phi, then that means that neither 0 or 1 were a part of the Borel sigma field, all right? And that omega is an empty set. Omega points nowhere, it's an empty set. If IA inverse B points to A, then 0, comma 1 and B is equal to 1. That means if it points to A, then that means the function IA of omega pointed to 1. All right, and 1 became the part of the Borel sigma field. Similarly, if it points to A complement, then that means I of omega pointed to 0, and 0 was what became the part of the Borel sigma field. And if IA inverse of B gave me a value both 0, comma 1, then that means omega was basically the entire set big omega, and it covered the entire Borel set, which is the real number line. And so 0, comma 1 and B gave me a value of the entire set big omega, all right? So now if you observe carefully, this forms a sigma field if in discrete time. So if you look at it, this is consistent with the rules of the sigma field that we discussed in the second video, right? So we've seen that the indicator function is a real-life measurable function, all right? And with this, I'll stop here. I just wanted to drive home the point of measurable functions and why it's important to start modeling everything on the real number line. And in the next video, I'll start with probability measures, all right? Probability measures for the measurable functions. So I'll see you guys there. Thanks.